Hello, in this video, I will talk about the tangent line, the limit idea, and instantaneous velocity. Okay? We will try to investigate and connect all of them together. Okay, that's it. In order to start this, let's try to define the tangent line. That's what really tangent line is. Probably we all understand and we know at least some intuitive definition. But looking at this picture, circle, and the line T, the pink line, we can definitely say that line T is tangent to the circle. And the definition that was provided, I think 300 years before current era, by the Greek mathematician Euclid. We all know that person from the history of mathematics. Euclid, he defined the tangent line as a line that intersects the circle once and only once. And this is correct because trying to draw a line that intersects a circle once, we will actually draw a tangent line. But when we will take a little bit more complicated or just different curve, this definition will not be exactly correct. It will be inadequate because the verb intersects it's not exactly proper. But yeah, for the circle, we can definitely use this. We know that tangent, we have this intuition that the tangent just intersect once, has one point in common with the curve. Okay, let's look at more complicated curve. I don't know if this will be really complicated, but a little bit different than circle. I have the curve C, and I draw the line, the pink line T, and the blue line L. We can focus on the point P. We may notice that line L, the blue line, intersects the curve once. But you will all tell me that this is not a tangent line. Now, line T, we have a little bit of issue because looks like a tangent line, however, intersects the curve twice. And I can label that point, let's say point Q. But what we will say, looking at the line T, the pink line, and just locally analyzing like point P, we may definitely say that line T is a tangent at the point P only. That we're not looking far away, we will just limit ourselves to the neighborhood of P. And as we can see, the pink line is definitely a tangent. Blue is not a tangent, because what we need, I have couple of notes. Let's see. That means T is definitely tangent. We agree this because one thing, from Latin, tangent means touching. That we can nicely see that line, the pink line is touching the curve. This one is actually intersecting. That means that's not good. It's not respecting the definition, the meaning. Looking a little bit more like mathematically, we can say that tangent line is a tangent if has the same direction, which the same direction and touching means almost the same as the curve at that point. Because when we will zoom in, when we will go even closer, we can see we cannot even distinguish the difference. That means tangent line and the curve, they behave exactly the same. They have the same direction, the same slope. I can use that magic word. Okay, and sometimes we even say in calculus class, slope of the tangent is the same like slope of the curve at that point, because we can see we cannot distinguish the difference. We know that tangent is sitting at the top, but no difference. Okay, that's when we good with the tangent. Tangent line is touching a curve at one point and has the same direction as the curve. Okay, that's me now. Let's actually start working. We know the definition, we good with tangent line. Now we have to find the equation of the tangent line to the parabola x squared at the point 1, 1. Parabola x squared, xy plane, point 1, point of the tangency, and the tangent line. And now, I believe we have a small issue, because in order to find, first of all, a tangent line, and having a point, we may use point slope form. Actually, that's not an issue yet. Okay, that in point slope form, it's convenient because we have point, we just need that magic quantity m, which is the slope. That's in point. I can substitute 1 and 1 in a minute. I can actually write down y value is, and this is slope of that line, and x value is 1. Okay, that's me. Now how we can find the slope, because that's the big thing. Normally slope we calculate, like we have to have rise and run. We have to have the changes in y, changes in x. Oh, let me just check something. Oh, okay, that means I can maybe say here slope of any line, even the tangent line, we need a rise and we need a run. That's we have to see how the line is changing along the y-axis and then along the x-axis. But and maybe I can just write the formula. This will be y2 minus y1 x sub 2 x sub 1. Or we can say f of b minus f of a. We know depends. A and b, of course, is respectively x sub 1, x sub 2. And the y's are the corresponding values. Okay, but we can see we do not have, we have only 1 point. That means I need to check, yeah, in order to find the slope. In order to find the slope, because it's not possible if I will just use 1 point. How we can find the slope between the point and itself? We will have 0 over 0 because both of them will be the same. Yeah? And I'm saying point on, like if I will draw a secant line, of course, then I will have 2 points. They will belong to the line and to the curve. That means it's not, first of all, we have to agree that it's not possible to find the slope between the point and itself. Because in order to find the slope, we need 2 points. We remember from algebra, like average rate of change, we have to have the y interval over the x interval. That's what we will do. Since we don't know exactly what to do, but we know algebra, we may find a point Q. I mean, the second point, we will name it Q. And maybe we can just work on the secant line. Yeah, that means I can find point Q somewhere here. Or we need the point on the curve because we don't have equation of we need the point. But now when I will connect these 2 points, that will be easy to find the secant line, the slope of the line. It will be secant, but it will be not exactly a tangent line. That means let's maybe do it. I pick the point. Okay, we can see, I pick the point Q, which is this point, of course, point of interest. And I pick 2 squared is 4. That's when I pick the point 2, 4. And as I said, it's easy because now we can definitely get the slope of the blue line. Yes, we can get the slope of the blue line, which actually is rise over run, as I draw this, and the values, and I can even draw here. 4 minus 1, that's rise, and 2 minus 1, 1, that's run. We can see just the difference because we have an interval along the x-axis and along the y-axis, 3. Okay. And we can see it's okay, but still that's not a slope what we want. But we at least use the tool that we know. Okay, that's now I can say it's fine, but how we can improve, because definitely we have to use this. We have to use this method, this tool, finding the slope. I'm saying this or any other equivalent form. That's what I did. Because I said I picked the point, the second point. And this will be always the case. We have to pick the second point because we cannot have like 1 minus 1, 1 minus 1. This will be 0 over 0, which, however, 0 over 0 is also a big deal in calculus. But we will talk about this later. Yeah? But we can see we cannot do this. That's when I actually I went away like 1 unit from 1, from that point, I pick 2. And we can see the blue line is, but now, if I will choose the point that is much, much closer to 1, and also create a secant line and calculate the slope, this will be really good approximation. Yeah, that's it. Let's look at this one. Oh, it's a little bit shifted, but let's pretend that this is point 1, and we're looking, of course, for that tangent line. Yeah, this is tangent. And now I went away 1 unit and I picked the point 2. X equals to 2, too far away. Now we can get closer. I can go maybe this one, 1.8. Maybe this one, 1.5. Maybe this one, 1.3. Or maybe even really close, I don't even have room, 1.00001. And now you can imagine if we will draw this secant line, it will be almost like a tangent line. And that's the point. Okay, that's when finding a tangent line, we're still using a secant line, but on the as much as possible, the smallest interval. The smallest changes. It's almost between 1 and 1, but of course we cannot have 1 and 1 because 1 minus 1.0001. That's we still create a rise and run. Okay? And this process, what I just show you, 1.8, 1.5, 1.3, 1.0001, we will call that this is the limiting process. Yeah, we kind of want to take 1, but we cannot algebraically. We're not allowed, like, divide by 0. Oh, too fast. Okay, and then I pick that value. That's me. Let's maybe do it. I use the calculator, which usually we don't use the calculators in calculus class for the concept questions. But I just used to show you, yes, like, because we don't want to deal with these numbers like without the calculators, but we have to get the tangent line at this point. Okay, so now let's look at this. What I pick, that's the values. We still have a point P, 1 and 1, point P, coordinates 1 and 1 for each of this example. That means this is 1, 1, 1, and this point I pick to be 1.5. This one is 1, this one will be 1.1, and we will get the slope. You can probably get easily 1.01. Maybe it's enough to be 1.01. And then the corresponding values are 2.25. This one will be 1.21, and this corresponding value, we just squaring 1.0201. Okay. And this one is 1. That's what we can see. You can nicely compute rise and run and find the slope. That's me. Let's find. Yeah, we can see that's rise over run, 2.5. Well, I use calculator. Yeah. Now another point. We can see that's the rise over run. I'm just doing for everything, for all of the cases. 1, 2, and 3. Okay, then we can see we compute the slope, it's 2.1. And then we getting even closer, and I compute the slope is 2.01. That's when you may guess, looking at these numbers, that's the slope of the blue line, 2.5, 2.1, 2.01. And if we will go even closer, 1.0001, we will definitely approach a slope with the value 2. Okay, that's when if I will go extremely close, if I will pick the point Q, like I just said almost 1.0, but we are on the right-hand side. Yes, just on the right-hand side at the moment on this slide. That's when 1.000001. We may notice that the slope will be 2. And actually, that's the good way to find the slope of the tangent. That's how the mathematicians were doing many years ago. Then they developed some patterns, shapes, and now we have lots of formulas, but we have to understand the logic, definition, meaning behind. That means this will be the slope of the tangent. And if we are asked to find the slope of the tangent, we will use the secant, that the coordinate x is approaching coordinate x of the point P. Yeah, because we can see, okay, 2 is the slope. Now I also did the calculation on the left-hand side. Let's look at this, because having the point P1, I think I pick 0.5, yes, and then rise and run. And then I pick I didn't change, 0.9, that means it's closer. That's the corresponding value. Of course, x squared, I'm just squaring, because if this is x, this is the value x squared. Okay, and still we're looking between 0.11 and the other, and we know how to find the slope if we have 2 points. That's it. Now we can see slope between the slope of the secant line, QP, between Q and P, Q being 0.5 and 1, it's 1.5. And then another slope, when we're getting closer to the 0.1 on the left-hand side, is 1.9. And then 1.999. And if we will go even closer, that point, I didn't change the graph because it will be really crazy, but we can see that's supposed to be a little bit more vertical. Okay, 1.9. And now you can also guess when we will go even closer to the 0.1, which is 0.999999, we will get the slope almost 2. Okay, that means we may consider now that that's our best approximation, estimation of the slope of the tangent, and this is 2. Okay, that's the whole process. That's what we have to do. If you will be asked again to find the slope of the tangent, find at the point like 1, 1, find a couple of points extremely close to 1 on the left-hand side, right-hand side, compute all of these slopes, and look where the numbers are, what the numbers approaching, what direction they go. Okay, now a little bit of formal terminology. That means, first of all, we found the slope of the tangent line using the slope of the slopes of the secant lines. But what we were doing, we took the limiting position of the secant line. That's what we will call the limit of the slopes of the secant line. Will give us the slope of the tangent, because we will get closer and closer and closer, but we do have that limit. We cannot go exactly at that point. Okay? That means the limiting position of the slope of the secant line is the slope of the tangent line. And now, symbolically, because limits, that whole process is the fundamental concept of calculus, we will use a lot. We have special notation. That means limits means we will just use this shortcut, LIM, limit, and always underneath the limit, we have to put the notation, but just underneath the word limit. Like what we were doing, what limiting action took place. We know that point Q was approaching, we can see that arrow, Q approaches P. Because we get closer and closer from the right, from the left. And now limit of what? Like we need this main thing, slope of the secant. This is just slope of the secant line between Q and P. That means I can actually write slope of secant line. This is this. And the resulting is slope of the tangent. Slope of tangent. Okay, excellent. And we will not say approximation, like we will just say is equal to, because behind the limit, it's hidden, that process, that meaning, that meaning of the limit. That we will still put equals to. Now, this is too much of different letters. We have to be able always to rewrite the limit in terms of the independent variable x. That's, let's see this. That's the same thing. And that's the same thing. Limit Sx, because x was the coordinate of the point Q, x, f of x. I was choosing like 1.9, 1.5, 1.1, 1.01. That means x was approaching 1. X approaches 1 because 1 was the point of interest, of tangency. We wanted tangent at 1, 1. That we can see, but everything x independent. And now this is just the definition of it's rise over run. It's actually slope of the secant. If we think this way, x squared is the value of x, and 1 is the value at 1, and x minus 1, because the point was 1, 1, and x squared. I can even remove this one because we know the formula. It was x squared. That means function was defined as a x squared. Okay, that's we can see that's actually just rise over run. And we know, I'm just using the previous 2 slides, we know that is 2. Okay, and now I can finish the question. Tangent line is 2x plus 1, because when we will use point slope, now I have the slope. And when we distribute everything, 2x minus 2, and providing the mx plus b form, we will have 2x plus 1. Because this, am I wrong? 2x minus 1? Of course, yes. I have to distribute 2x minus, now it's lucky that I did this. Too fast. Let me just check. And we can even, I think this is because it's positive slope. We definitely know that it's positive. It's minus 1. It's good that I write this. This was typo, of course, typo. Because it's minus 2, and when we add 1, minus 1. Okay, that's just, But the point is to find the slope. That's mean now you know how to find the slope of the tangent line. This box, these words are really important. Slope of the tangent line is basically the limiting position of the slope of the secant line. We have to find a couple. Okay, now I also have one extra exercise. Okay? Like example number 2, velocity problem. We also know that finding the average velocity, like speed, speed is the absolute value of the velocity. Velocity could be positive or negative, depends if we're going in the forward or backwards. That means average velocity like this is not a problem. We can find without the calculus. We just need a distance over the time and no problem. Like for instance, I'm driving 150 miles in 3 hours. My speed will be, or velocity I can call speed. It's the average rate of change of the distance with respect to time. It will be 50 miles per hour. Per is the fraction bar. No problem. But now, if I'm driving for 3 hours, doesn't mean that I'm driving all the time 50 miles per hour. Like I will drive a little bit faster, a little bit slower. That's me now. The question is, what is my velocity like exactly maybe after like half an hour? Like exactly at maybe after 1 hour. We know that the speedometer is showing us this in the car, but it's definitely a calculus, the use of calculus. That's me how I can find my speed exactly, is exactly at one point. And this is average rate of change of the distance with respect to time. This will be called instantaneous rate of change at that instance. At that moment. And again, at that moment, if we think we have no distance, because when you will take a picture of somebody driving, you will have 0 miles over 0, like minutes, seconds, hours. So we can see again 0 over 0. No, but what we may do, this average rate of change is exactly the same exercise like finding the slope of the secant line. Instantaneous rate of change, instantaneous velocity, it's exactly the same process like finding a slope of the tangent line. Yeah, and I don't want to say that's what we will do. It's not exactly 0. Like let's say 0.1, 0.1. We still have to find a teeny tiny time interval. Yeah? Maybe like taking a picture with the smartphone. Now we have these live pictures. Yeah? Like you will see the tiny movements of the car, even on the still picture. Yeah, you will see that we have to calculate what was the time, which will be 0.0000 probably second, and even the distance, like the wheels probably moved a little bit. We have to calculate that inch or like a really small percentage of the inch and divide, and we will get a big number. Unless you're driving slow, we will get a smaller number. Okay, but let's finalize and let's connect this. That means this is one thing, easy, algebra. Slope of the secant line, in general, is the average velocity. Yeah. Rise over run, we will have this. We can see point P, point Q. We can even have some 160 miles, 10 miles. That means this is 150 and this is 3 hours. Of course, the same thing. My average speed is 50 miles per hour. And that's correspondingly the same thing for the secant line. Yes, that means slope of the secant line is the average rate of change or average velocity, which is also rate of change of the distance with respect to time. But in general, any average. Okay, now the calculus part. Slope of the tangent line will represent the instantaneous rate of change, instantaneous velocity, if we're talking about distance over the time. Yes, that's mean, and we know the process. We have to find the tiny, yes, if we would like to find out, oh, let's say this is 1. This is supposed to be 0. Okay, that's, let's say this is 1 because we just said 1. That's, we will go away like 3, maybe it's too far. I mean, could be 2, but let's just put 1 tangent line at 1. Could be 2, but I just want to correspond to this one. That maybe we can go 3 away. Maybe we can go, we can see P. We have to find, yeah, like the X, the time, we can put from 1 to X. And we know, because we did the X squared and the tangent line. That's when we're trying to get closer and closer. Even this one is too far. We want somewhere here, really close. And then that slope of this tangent will, slope of the secant will definitely represent the slope of the tangent. That's, we know this, I just want to clarify that slope of the tangent line is the same thing like finding instantaneous velocity. Okay, please remember this. And of course, slope of the tangent from the previous exercise, from the previous example, is the limiting position of the slope of the secant. Okay. That's the 2 things that we have to take away from this session. Let's finalize with this question, with this exercise. I have 3 exercises, but exercise 1 we will do together. Exercise 2 and 3, you will do it on your own to check if you understand. Okay, use this graph presented below to find the sum, okay, the sum of instantaneous rate of change at 7 and average rate of change between 0 and 2. So now we have to calculate this. This is y, this is x. Okay, instantaneous rate of change, of course, is the slope of tangent line. That's 2 things that we have to take away. Slope of the tangent. Okay, 7. This is 7, and this is approximately the tangent line. We can see this slope is definitely 0 because for the horizontal line. Horizontal line has the slope 0 because it's no rise. And that's this, okay? That's this will be 0. We have this number. Now we need blue. Average rate of change, we just need 2 points. 0, this is the corresponding value, 2, this is the corresponding value. Beautiful. Tangent line. I mean, that's actually not a tangent. Secant line is actually that line. That means slope of this line, I can actually say slope, oh, P disappeared, of secant line. That's what I want my students to know. Instantaneous rate of change, slope of the tangent. Average rate of change, slope of the secant. Okay, and this one is definitely negative. 4/2, -2. Everybody can get this. Okay, and we just need the sum because this is the question. That means sum will be of these numbers 0. And then, let me be consistent, plus -2. Okay, the final answer is, of course, -2. But the most important was the red value and the blue value. Instantaneous rate of change, again, slope of the tangent, average rate of change, slope of the secant. Excellent. Thank you. Now I can quickly show you exercise 2 and 3. You will try to do it together. You can do it less than a minute, both of them together. Okay, let me put this. That's it. Thank you. And please enjoy your concept of tangent line. Thank you. And yes, check the next video. Thank you.